Hello. Today we'll be learning about how to use logic gates and logic circuits to tackle one of the most basic and crucial functions a computer can do, addition. So first, let's analyze what we're going to do. We're going to build a circuit that adds 4-bit hexadecimal numbers and produce a result. Something odd you may notice is this column right here. We know that D is hexadecimal for 13, and 6 is just 6. How is that 3? Well, if you think about it, when those two numbers are added together, we get 19. And that is turned into hexadecimal is 1, 3 in hexadecimal. And due to the limit on bits, see here we only have 4 bits, we have to take out the leading bit, which is the 1, and have a result of 3. So let's do this in a more binary way. So what we want to do is, for example, we have two numbers. We want to add them and produce a result, which here is 1, 0, carry 1, 0, carry 1, 0, 1. And in this case, we take out the leading one, just as we saw it before. Before we can do this, we need to understand the concept of a half adder, an adder that adds two numbers and produces a result. So for example, let's say we have a result. Let me open the Blackboard instead. So for example, we're gonna have a input A and input B, those are just bits, and we want to produce a result. When we construct truth tables in this case, well, since A and B are just bits, it would result in a truth table. So when we construct a truth table, we write out all the possible combinations and the result. So for example, here, the results will be 0, 1, 1, and 1, 0. Remember in the previous case, we actually used this carry in addition that we would need in further cases. So we can just dump this bit. So instead what we do is we transform the result into a pair of numbers. The first number is a carry out, and the second number is the sum. So for this case, the carry out will be 0, 0, 0 for the first three cases, and 1 for the last case, and the sum will be 0, 1, 1, 0. So now the problem becomes, how do we get from A and B to our carry out and our sum? So if you take out the truth table and look at only these three columns, we can see that C out is only 1 true when both A and B are 1. And that is a characteristic of an AND gate. So we get from A and B to C out using an AND gate. Now what about the sum? We can see here, taking into this column, we can see that sum is 1 when either A and B are 1, but not both. And that will be a characteristic of the XOR gate. So we can get from A, B to sum with an XOR gate. So moving back to the slides, this is a more pretty truth table of what we're trying to construct with the truth table. And this gives us the input. The input as A and B, and the results are S and C, where S is the sum and C is the carry out. So let's actually build this in this beautiful app called logic.ly. So let's start simple. What do we need? Well, we need a bit for input A. We need a bit for input B, Come on. And we need two results. This result will be the sum. And this would be the carryout. We'll just call it C here. And like what we said before, we used an AND gate to get from A and B to the carryout. So let's fetch ourselves an AND gate, feed those data in. So A and B gives us the carryout. And now moving on to the sum. Like we said before, we achieved the sum using a XOR gate. So we can just move that over here, feed both data in, A and B, XOR gives us the sum. So let's test this out. If we have A and B both as 0, the results are both zeros. In this case, that will be true. If either one is a 1, the sum should be 1 and the carryout should be 0 also. So let's test that. If we, yes, the sum is indeed 1, and for B, the sum is indeed 1. And the final case is when both inputs are 1, in which we would have a result of carry out with 1 and a sum of 0. So let's test that, and we're good. So for easier use in the next example, I will select this, edit, create an integrated circuit with this thing. We'll call it a half adder. And we'll talk about why it's called a half adder in the next example. And now we have a half adder here. Okay, thank you. Let me know if you have any questions.